hopefully.
Ah. So thanks a lot for sticking and coming for the second lecture in a row. Um, this is about the same topic again, conjugacy classes in algebraic groups. If you remember from last time, we are following this very nice article by Springer and Steinberg. The title of the article is Conjugacy Classes, and this is from the proceedings of the seminar on algebraic groups and related finite groups. And I told you last time also that for more details, one may look at these two very nice books by Steinberg. The first one is Lectures on Chevalier groups, and second is Endomorphisms of Linear Algebraic Groups. Let's just recall very quickly our setup. We are working with a connected semi-simple group over k equal to k bar. So in the previous lecture, in the last lecture, for some of the things that I did, it was quite okay to consider a reductive group instead of a semi-simple group. But in today's lecture, I am going to clarify a few things where semi-simplicity is needed. And for such a group, we define this subgroup G sigma. So whenever you have an endomorphism of the group G, then for this endomorphism sigma, we take the fixed points, and that's a subgroup which we denote by G sigma. If you are working with a field whose characteristic is positive, and if you take sigma to be the Frobenius endomorphism, which corresponds to Q equal to some power of the prime P, then this G sigma is a finite group. I explained this very briefly last time. You can consider these are linear algebraic groups, so they are sitting in some matrix groups. And then the Frobenius endomorphism simply amounts to raising every power to the qth entry, every entry to the qth power of the corresponding matrix. And when you are looking for elements which are fixed by this Frobenius endomorphism, then it should correspond to matrices whose each entry comes from the finite field FQ. So G sigma is sitting inside the corresponding subgroup of the matrices, which is defined over FQ, which has all entries coming from FQ. So it's a subgroup of a finite group, and therefore this G sigma is a finite group. And this final comment is that the finite groups of Lie type, they are all obtained in this way. That means you start with a connected semi-simple group over algebraically closed field of characteristic P, which is positive, and you apply Frobenius endomorphism together with some possible twists. So these twists are given by either the diagram automorphism. So your semi-simple group will have corresponding root system, and then there is the Dynkin diagram, which will have its own automorphism. So there could be diagram automorphisms, and in some very special cases, there could be field automorphisms. So some field automorphisms give rise to endomorphisms of the group G, and those are the ones that we also consider together with this Frobenius endomorphism. So this is how all finite groups of Lie type are obtained, and this is explained very nicely in the book by Steinberg that I mentioned, the lectures on Chevalier groups. So that is one nice book that one can read and learn quite a bit of this. Now we are studying conjugacy classes. So this is one very important result that we are going to use. This is the Jordan decomposition. Let us, this is a very, very interesting result. We are going to use it once again in the lecture later part, and I will explain it again that time. So this says that whenever you have a group G and there is an element G in G, then there are these two elements, one of them being semi-simple, the other unipotent, and the unipotent and semi-simple elements commute with each other, and therefore they also commute with G being the product of these two. And once you have these properties, then the elements S and U are unique with these properties. So semi-simple element and unipotent element can again be defined by considering some faithful representation of your G inside a matrix group. Now, I explained it last time that this decomposition remains valid under any homomorphism. you have a group G and you have another group H, and you have a homomorphism, then the image of G has its semisimple part to be the image of S, and the unipotent part is the image of U. Therefore, especially if you are looking at endomorphisms, you are looking at homomorphisms from G to G, then also this decomposition remains valid. And so whenever you have G sigma, the points which are fixed under sigma, in that subgroup also there is this decomposition. By that I mean that when you have G inside G sigma, then the corresponding S and U are also in G sigma. So you have a Jordan decomposition which goes through all these processes. Moreover, it gives this very nice computation that when you are looking at centralizer of your element G in capital G, then this will then be automatically, if anything commutes with S and U, it will commute with G. Therefore, the centralizer of S intersection centralizer of U is contained in centralizer of G. And we further have, which is something that I have not mentioned here, that S and U can be written as polynomials in G inside the matrix ring. If you are putting your G inside a matrix group, then you consider the corresponding ring of matrices. In that, the polynomials make sense, and S and U are polynomials in this G. Therefore, if you have something which commutes with G, it is going to commute with S and U. So we have the first equality, that centralizer of small g is centralizer of small s intersected with centralizer of small u, and that then gives that you have to look at centralizer of u inside another smaller subgroup, that being the centralizer of S. So these centralizers of semi-simple elements are reductive groups. Therefore, if you understand all semi-simple centralizers, and within those, if you understand all unipotent centralizers, then using Jordan decomposition, you will have understood all centralizers. Or in other words, this theorem allows us to reduce the study of conjugacy classes of elements in G to the study of semi-simple classes and unipotent classes. Now, in the previous lecture, I told you quite a lot about semi-simple classes. I would like to clarify a few things from that, and then we will say something about unipotent classes. So this first statement is very natural. This holds over algebraic closure. The semi-simple conjugacy classes in G are in natural correspondence with T mod W. The while group, being the normalizer T upon T, acts on W, and you look at the orbits of this while group action in the torus T, that those orbits correspond to the semi-simple conjugacy classes in G, and we have used Bruha decomposition in this. And moreover, this statement, which I again make, that when G is semi-simple, then the centralizer of this semi-simple element is a reductive algebraic group. Now, so in the last lecture, we had some confusions about some statements. So let me again mention these here. The theorem is that if your G is simply connected and you have a torus T which is fixed by sigma, then the semi-simple classes in G sigma is in natural correspondence with T by W sigma. So what this means is the following. We are looking at a semi-simple connected algebraic group and assume that it is simply connected. And you take a torus in this group above, which is fixed by sigma as a set. Okay. Then the above statement already tells you that the semi-simple conjugacy classes in G are in correspondence with T by W. This is valid for any maximal torus. In particular, this is valid for our torus which is fixed by sigma. Then the semi-simple classes in G sigma. So there are two things that are happening here. Number one is that we have a class in G which is semi-simple, and as a class this is fixed. So we are looking at sigma being the endomorphism of the linear algebraic group G, It will act on subsets of G, and we are looking at classes. So one class may be sent to another class, or a class may be invariant under the action of sigma. So whenever you have a class which is invariant under the action of sigma, there is a result which I mentioned in the last lecture, that such a class contains an element which is fixed by sigma. So if you have a class capital C which is invariant under the action of sigma, that means sigma takes C to C. Then C contains an element X with the property that sigma of X is X. So this X becomes an element in the G sigma then. But it is quite likely, and we have actually seen possibilities, that you may have another element Y which is in G sigma. Y may not be conjugate to X as an element in G sigma, but it may be conjugate to X above, which means to say that the conjugacy class of Y in the algebraic closure may be equal to the conjugacy class of X. So when we are computing the conjugacy classes of elements below, we will be looking at the conjugacy classes which are fixed by sigma above. And for each such conjugacy class, we have to see how many conjugacy classes it gives you below. And this is where the simply connectedness comes into picture, because for simply connected groups, for each conjugacy class above, there is a unique element below. So to look at semi-simple classes in G sigma, it is enough to look at the conjugacy classes above, which are fixed by sigma. And this is valid for simply connected groups. And that is then given by T by W sigma. So let's just do an example of this. So the number of semi-simple conjugacy classes in SLNFQ is q power n minus 1. So SLN is something that we understand very well, and this is something that we may also be able to do in one of the tutorials for very simple n's, maybe n equal to 2 or 3. But this statement alone is very easy to prove, because when you are looking at matrices inside GLNFQ, then they have some certain characteristic polynomials. Okay. Now we also know by the notion of companion matrices that whenever you have a characteristic polynomial, whenever you have a polynomial which is monic and of degree n, then there is a matrix whose characteristic polynomial is this polynomial. Moreover, if your last entry, the constant term, is minus 1 power n, then the corresponding matrix will be in SLN. So if you were looking at matrices inside SLNFQ, all you have to look at are the characteristic polynomials which are whose constant term is minus 1 power n. That's the determinant value. Now, we see that whenever you have a characteristic polynomial, and if your corresponding matrix is semi-simple, then there is a unique such class. Okay, so if there are two diagonal matrices which have the same characteristic polynomials, then those matrices are conjugate inside SLN or inside GLN. Therefore, to look at semi-simple conjugacy classes in SLNFQ, all we have to do is to count the number of characteristic polynomials. The only possible characteristic polynomials that you have will have fixed the highest degree term, the leading term, which is 1, and the constant term. So degree n term is fixed, degree 0 term, the constant term is fixed, but there are no conditions on the in-between terms. So degree 1, the coefficient of x square, all the way up to coefficient of x power n minus 1. There is no condition. You can have any entry there from the field FQ, and therefore the number is now q power n minus 1. So it's a very easy proof to say that the number of semi-simple conjugacy classes in SLNFQ is q power n minus 1. Although it would be interesting still to do it for SL2, SL3, actually computing the conjugacy classes or writing them down. And the same proof remains valid when you replace your SLN by a connected, semi-simple and simply connected group. This was the correction which was pointed out by Dipendra, and I I'm very thankful to him that
In
he
fact, Shripad,
corrected
even
this
here
mistake.
that will play a role. Shripad,
Sorry.
even here that confusion will be there, that you may have two matrices in SL and FQ which are not conjugate in SL and FQ, but they become conjugate in bigger field. You know, you stated this result about GLN, that conjugacy in GLN, FQ and FQ bar are the same. So
Um,
conjugacy in SL and FQ, it may not be conjugate in SL and FQ, but in GL and FQ they may become the same, and therefore counting the characteristic polynomial will not be. You need to do little more.
but for semi-simple,
That's what it is true, but it is not. I'm just saying that a little more has to be done. No, it's not such a difficult step, but I'm just saying that one has to
okay,
observe what you said for GLN, that two matrices in GLN FQ are conjugate if and only if they are conjugate in GLN FQ bar. Same is true for
okay,
SLN for semi-simple matrices, and that needs to be
yes,
observed. I'm just saying that
okay,
that needs to be observed.
okay. Um, so the reasoning that I gave, that is incomplete. One needs to say something more.
Something little more, that two
So
matrices in
essentially, to
SLN.
say that each characteristic polynomial gives you only one conjugacy class, that has to be explained.
Correct. That's all.
Okay. Yes. But I was going to give a proof in general. So if we replace SLN by a G which is connected, semi-simple and simply connected, then the same result holds, that you have a semi-simple conjugacy classes in G sigma. This is Q power R, where R is the rank of G. So for SLN, we observe that the rank is nothing but the dimension of the maximal torus, and you have the diagonal torus. So alpha 1, alpha 2, alpha n, with product of alpha i's being equal to 1, that has dimension n minus 1. And so this statement, the highlighted statement, is the general case of the above statement. And I have some steps to see how this can be seen. So, of course, the first statement is again repeating the statement that we have above, that semi-simple conjugacy classes correspond to T mod W. Okay. Now, this second statement is something which is very important. If you look at T by W, this is an algebraic variety whose coordinate ring is CG, the algebra of regular class functions on G. So again, this is true for any semi-simple group. You are looking at T mod W. W is a finite group. T is a variety. And so the quotient is again an algebraic variety. And its coordinate ring is nothing but the algebra of regular class functions on G. Regular class functions on G. This next statement is again valid for any semi-simple algebraic group, which is that the CG, it's a huge ring, it's an infinite dimensional ring. It has basis over the base field K, consisting of irreducible characters of G. So this is quite natural. You are looking at regular class functions, and the class functions are all spanned by irreducible characters if you are working over algebraically closed field, and G is semi-simple. And this next statement is very important. I think this will take care of what we were saying in the last slide. When G is simply connected, CG is generated as an algebra by the fundamental characters. So maybe I could take 1 or 2 minutes to explain what these fundamental characters are. So our G is a semi-simple algebraic group, and therefore we have the root system which is sitting inside some Rn. Okay, and then there are weights. So we take all possible vectors which have integral inner product with the roots. Those are the weights. That is again a lattice, and there is a very particular basis for this lattice called the fundamental weights. Then for each fundamental weight, after having chosen a simple system and all that, for each fundamental weight, we have a representation whose highest weight is that fundamental weight. And then the corresponding character of that fundamental representation is called the fundamental character. So CG is a polynomial algebra on these are linear algebraically independent functions. Therefore, it's a polynomial algebra in R variables. And therefore, in this case, the highlighted case, when we have G to be simply connected, there we have this isomorphism that T by W is now isomorphic to affine space of dimension R. That is because the coordinate ring is a polynomial ring in R variables. So when we apply this to our example of G being SLN, then we will see that T by W is isomorphic to A power n minus 1. And now this is an affine space. We have sigma fixed points on this will be the affine space over FQ power R. And then it is easy to compute that the cardinality of this is Q power R. Okay, so once again, to say this in other words, when you have semi-simple algebraic group, every class above which is fixed under sigma has an element which is fixed by sigma. And whenever G is simply connected, this second last statement is equivalent to this, that whenever G is simply connected, each such class has only one conjugacy class below. Therefore, counting the elements which are there with counting the number of conjugacy classes in G sigma, which is semi-simple, is same thing as counting the number of conjugacy classes above, which are fixed by sigma. And that number is now given by A power R fixed by sigma, and therefore its number is Q power R. So this is some kind of proof. This is again there from Springer and Steinberg. This was some confusion last time, and I think even maybe now this proof is complete, although maybe the reasoning given for SLN is not quite complete, because we have to say that whenever two elements are conjugate in GLN, so what happens is that when you have two semi-simple elements with the same characteristic polynomial, they are conjugate in GLN, and we want to say that they are conjugate in SLN. And as Deependra says, it does require some reasoning. Okay, so let's go and do one more important thing, one or two more important things. So I want to say something about centralizers of semi-simple elements. So let's say that we have a fixed maximal torus, capital T inside G, and we have a subset S of this maximal torus. And we have the root system sigma and the while group and so on. So let sigma prime be the set of roots which vanish on S, which are trivial on S. Vanishing meaning they are trivial on S. And let W prime be the centralizer of S in W. So W prime is the normalizer of the torus. It will act by conjugation on the whole torus. But when we are given a subset S, we can look at all elements in W which act by as identity on S. It's not sending S to itself. We are not looking at normalizer of S. We are looking at the elements which are fixing each element in S. Then the centralizer of S in G is generated by the torus T. The U alphas, remember that these are the root groups. Whenever you have a root alpha, there is a one parameter subgroup of one, there is a unique one parameter subgroup inside G corresponding to this root alpha on which your torus T acts appropriately. So the centralizer of S in G is generated by your maximal torus. Maximal torus has to be there in the centralizer because it's a commutative subgroup of G which contains S, so it will definitely be centralizing S. And U alphas, whenever alpha is in sigma prime, alpha vanish on S, so the value of alpha on S is 1. And we know that the torus T is acting on U alpha by the character alpha. So again, U alpha is something which is there in the centralizer. And once again, the NW, where you have the W is coming from W prime. Again, W prime is the centralizer of S in W. W prime is the set of all elements in W which fix each element of S under conjugation. So you take the corresponding NWs. All these have to be there in the centralizer. But the nice thing is that the centralizer is also generated by these. So the centralizer of your subset capital S in G is generated by the torus T, the U alphas for the roots alpha which vanish on S, and the while group elements. You may just consider them to be while group elements where these elements centralize S. This is about the centralizer of the whole S. If you want to look at the connected component, then the connected component is generated by T and the U alphas. The NWs are not needed. And therefore, when you have a U alpha, the corresponding U minus alpha is also there. If you have sigma prime is a subset of sigma, which is invariant under alpha going to minus alpha. And sigma prime is also closed under addition. If you have alpha in sigma prime, if you have beta in sigma prime, alpha plus beta is a root, then alpha plus beta will also vanish on capital S. So all this will tell us that the connected component of the centralizer of capital S in G is a reductive subgroup, and its root system is sigma prime. So in particular, if we were looking at a single element X, then assume that your element X is semi-simple, put it inside a maximal torus and use this recipe to generate its centralizer. And then that will tell you that your connected component is a connected reductive group. Otherwise, it's a possibly disconnected but reductive group with the root system given appropriately. Okay. Now, this is a very, very interesting result. So maybe I can attempt to give the proof of this. So there is one very nice result which says that if your group is simply connected, then the previous centralizers that we have taken, they for singleton X are already connected. So if your group G is simply connected, then these semi-simple centralizers are connected. And one may ask, what would happen if your group is not simply connected? And this result explains it very nicely. So if it is not simply connected, if your group is not simply connected, then it will have a simply connected cover. So this G tilde is a simply connected cover, and you have this natural projection from G tilde to G. And suppose N denotes the kernel of this projection. So N is a finite central subgroup of G tilde, and G tilde being reductive or semi-simple, the N has to consist of semi-simple elements. Okay, so this is our setup, that we have a semi-simple group, and G tilde to G is our universal cover, which is denoted by the map pi. And let capital N denote the kernel of this map pi. Now, when you have a semi-simple element X in G, Gx upon Gx naught. Now I am suppressing the subscript G here because we are computing the centralizers only in G. For any semi-simple element X, the quotient Gx mod Gx naught, or the group of connected components of the centralizer, this is isomorphic to a subgroup of capital M. This is a very interesting statement. So at one go, it tells you what are all possible connected groups of connected components of any semi-simple element in a given group G. Okay. So for instance, if you were looking at SL2 and SL2 is simply connected. So suppose you look at PSL2 and assume characteristic is not 2, then you have this universal double cover. The capital N will have order 2. Then you know that any centralizer, any semi-simple centralizer can have at most 2 components. If you were looking at PSL3, then any semi-simple centralizer can either be connected or it can have 3 components. It cannot be that you are looking at PSL3 and you get a semi-simple centralizer which has 2 connected components. That is not possible, because Zx mod Zx naught has to be subgroup of mu3, the cyclic group of order 3 for PSL3. Okay, so for general semi-simple algebraic group, we have this statement, and in particular it tells you that this quotient has to be abelian. Now, if you have a semi-simple element X, there is no need, of course, that the centralizer is abelian. You know, we have seen that the centralizer is reductive, and we in fact computed some of them in GLN. When you have distinct some conjugacy classes, some eigenvalues are same, then you get the full GLN for that block. So it is not abelian. However, this quotient is abelian. It is finite is no big deal, because we know that the group of connected components is finite, but this is abelian, which is quite a big deal. And moreover, it consists of semi-simple elements because it's a subgroup of n. So these are all the possibilities. So that would mean that the representatives for the connected component of the centralizer can be chosen to be only of the semi-simple elements. This is all that we can read from here, and the proof is quite easy. So once you start with a semi-simple X, you choose any inverse image in G tilde under the map pi. Okay, so we have chosen this X tilde, which maps to X. Now we will define a map from Zx to N, and the map is defined in the following line. If you start with a G in the central, so this should have been small x. If you are starting with a G in the centralizer of small x, you take again any lift of G, which is G tilde, and take the centralizer. You take the commutator. So this G tilde X tilde, we claim that this G tilde X tilde is in N. So number one, since you are your capital N, which is the kernel of pi, that's a central subgroup. And if you were taking any different lifts, if instead of X tilde you were taking X1 tilde as a lift of X, and for G you were taking G1 tilde, then the commutator G1 tilde X1 tilde will each G1, the G1 tilde will differ from G tilde by a central element. X1 tilde differs from X tilde by a central element. So when you take this commutator, the central elements will all come out and they cancel out, and so you get the same element G tilde X tilde. So because your N is central, this element is well defined. It does not depend on the choice of X tilde or G tilde. Moreover, if you apply pi to the element phi G, now this phi G is in G tilde because you are taking G tilde and X tilde in G tilde and you are taking commutator. So phi G is an element in the universal cover. But if you apply pi to that, pi being a homomorphism, the image of phi G will be pi G tilde pi X tilde, which is G comma X, and that is trivial because you are starting with G in the centralizer. Okay, so phi G is actually an element in capital N. So this is very basic. We have not used any higher advanced theory. This is simply looking at some basic group theory. We are starting with a centralizing element of small x. You choose any lift of G, choose any lift of X. You may fix that lift of X in the beginning and take the commutator G tilde X tilde. That is an element which is in the kernel of pi. Now, we want to say that the kernel of the map phi is the connected component Zx naught. This is what we would now want to say. We have defined a map from the centralizer to capital N. And we want to say that the kernel of this map now is the group of connected, the group which is the connected component of identity element. This is what we want to say. So first of all, if you were to take an element in the kernel, so if your phi g is 1, that would mean that g tilde is in the centralizer of x tilde. Correct? Because phi g is nothing but the commutator of g tilde and x tilde. Remember, you have fixed x tilde already. So the phi g being 1 means that your left commutes with x tilde. So your left is in the centralizer of x tilde, but it's a kernel. That means it is again sitting inside capital G. So your left G tilde commutes with x tilde. Such is your G. So your G has to be image of that G tilde. And so therefore, the kernel phi is precisely the image of centralizer of x tilde. Because your G tilde has to be something which commutes with x tilde. Okay, so kernel phi is precisely the image of centralizer x tilde. Now, centralizer x tilde is a connected group because G tilde is simply connected. G tilde is simply connected, x tilde is semi-simple. Remember that when you are looking at these maps, when the kernel is itself is semi-simple, the x tilde has to be a semi-simple element. Okay, so x tilde semi-simple, it is an element in the simply connected group. Therefore, its centralizer is connected. Image of the centralizer is also connected because it's an image of a connected group. Therefore, this pi g x tilde is contained in the connected component of identity inside gx. Okay. So kernel phi is contained inside gx naught. On the other hand, your phi is a map from the group gx centralizer to a finite group. Capital N is a finite group. And when you have a finite group, its connected component of identity is the trivial element. And therefore, gx naught, which is a connected group, can go only to the trivial element. So that tells us that gx naught has to be contained inside kernel phi also. So we have gx naught contained inside kernel phi, which is contained inside gx naught. So kernel phi has to be equal to gx naught. So this map phi gives you an isomorphism of gx modulo gx naught to a subgroup of capital N. Okay, so once again to repeat the statement, when you take G to be a semi-simple algebraic group, perhaps simply connected or not simply connected, then Gx modulo Gx naught, this is isomorphic to a subgroup of capital N, which is the kernel of the universal cover. And therefore, it is abelian and consists of semi-simple elements. Moreover, you may ask that this result is true for simply connected groups, that the centralizers of semi-simple elements are all connected. Now, if your G is not simply connected, do you still have this result? That you take a semi-simple element and you take any semi-simple element in your group and the centralizers are again connected. Is that possible? And the answer is no, that is not possible, because all subgroups of capital N can be realized in this way. So if your G is not semi-simple, simply connected, then you have a non-trivial universal cover, you have a non-trivial subgroup capital N, then all subgroups of capital N can be realized as Gx modulo Gx naught for some semi-simple x in G. I think this will be nice to do it for some of the simple-minded groups, and we will try to do it in one of the tutorials. Okay, so this was about semi-simple elements. I thought these were some of the very, very interesting results, and it's again from the same article by Springer and Steinberg. And you can imagine what the reaction of the audience would have been when these results were presented. Some very, very interesting results. Now we are going to unipotent elements, but unipotent elements are very difficult to understand. And then what one does is that one understands a very specific subset of unipotent elements called the regular unipotent elements. So we are going to make a study of regular unipotent elements, but it is also possible to do a study of regular elements in general. Okay, and so we will spend some time on regular elements now. So when you have some, is there any comment? I may just take a call to see if there is any comment on the things that we have done up to now. Okay. All right. So when you have an element X in G, what we do is that we compute its centralizer. The centralizer is a subvariety. It is a closed subset of group G, and the dimension of subvariety does make sense. So all possible, of course, it's a subgroup of S, G. It's a subset of G. Therefore, its dimension is bounded above. And you will look at all possible dimensions. And whenever the dimension is minimal possible, then we call the element X to be a regular element. So an element X in G is called regular if the dimension of its centralizer is minimal. And when G is a semi-simple algebraic group, this minimal value is equal to the rank of the group G. And there is a very nice, very cute proof of this value also. One can show that this minimal value is less than or equal to R, and it is also bigger than or equal to R. It basically involves in putting your X in a Borel subgroup and studying what the rank can be when you are looking at it inside a Borel, what the dimension of the centralizer can be if you are putting it inside a Borel. Now, if your element is regular, then the connected component of its centralizer is an abelian subgroup. So there are many nice results that are there for regular elements. So if your X is a regular element, it may be a semi-simple element, it may be a unipotent element, or it can be a general element, which is neither semi-simple nor unipotent. But if it is regular, then Gx naught is an abelian group. Okay, so your group is almost an abelian group. Your centralizer is almost an abelian group. Moreover, if G is SLN, then these are some very easy statements that one can, we actually have done some of these in our tutorials without realizing. So if your X is in SLN, which is regular and semi-simple, then we are asking that the dimension of its centralizer be minimal, okay, and that be equal to R. We have computed the centralizer of semi-simple elements in SLN. We know that if there is any repetition of the eigenvalue, then you get the whole GLN block there. Okay, and then you get some products of GLN blocks, GLNs, and then the dimension of this centralizer is not equal to the dimension of the maximal torus. Therefore, if you want the dimension to be equal to the rank of the group, you should have all eigenvalues to be distinct. Moreover, if all the eigenvalues are distinct, then again this was something that was seen in the tutorial, that the centralizer is nothing but the diagonal torus. So when X is a regular semi-simple element, it is equivalent to saying that its centralizer is the maximal torus, and it is equivalent to saying that its eigenvalues are all distinct. Further, if your X is regular and unipotent, this is something that we have done for SL2 and SL3. We did not do it in general, but I asked you this, the last but one question was on this, that if your X is regular and unipotent, then this is if and only if its Jordan normal form consists of a single block. So you have ones on the diagonal and ones on all the super diagonal entries. An element being regular and unipotent in SLN is equivalent to having the Jordan normal form of this type. And moreover, if your element is regular in SLN, if and only if the minimal polynomial is equal to its characteristic polynomial, if and only if Gx consists of polynomials in X. So you put your your group inside a matrix ring, and there you can evaluate polynomials on your elements, and you look at polynomial values of capital X of your element X, which are again in SLN. Those are precisely the elements which will commute with your element X. These are some statements which are easy to see for SLN. And there are similar statements which we would have in general, which is that first of all, X is regular if and only if XU is regular in Gx naught, Gxs naught. So your X decomposes as Xs into Xu as the semi-simple part and the unipotent part, and Xs and Xu commute with each other. So when you look at this centralizer of Xs, your Xu is an element in this centralizer Gxs. Moreover, we have seen that Xu cannot be not inside Gx naught, because Gx by Gx naught consists only of semi-simple elements. That is something that we have already seen. So Xu goes and sits in the connected component of identity of the centralizer of the semi-simple part. Okay. Then your X is regular if and only if the corresponding unipotent part has, in some sense, the very standard structure, very standard Jordan normal form structure. If your Gxs naught happens to be some SLN, then Xu has to be that particular block matrix. So once again, the Jordan decomposition helps us in understanding even the regular elements in general. And for just as we have done in the previous slide, the results equivalences of regular semi-simple elements in SLN, we have such equivalences here for semi-simple elements, that when you have a regular semi-simple element, the connected component of its centralizer has to be torus. In the previous case, we were inside SLN, which is simply connected, and therefore Gx is Gx naught. So there we had that the centralizer itself would be torus. But in general, we will have the connected component to be a maximal torus. I should have said maximal torus. It has to be maximal because you are looking at semi-simple element. Then Gx will have to contain a maximal torus which contains your element X. And the maximal torus being connected, it will also go and sit in the connected component. So this is a maximal torus. And that means that X is contained in a unique maximal torus. There cannot be two distinct maximal tori which contain your regular semi-simple element. So this is something which is very nice, and we have a slightly similar statement for unipotent elements also. Okay, so X is contained, a regular semi-simple element is contained in a unique maximal torus, and moreover, if your X is contained in a unique maximal torus, it has to be regular, because then its centralizer connected component will have to be equal to that particular maximal torus, and therefore the dimension is the rank of the group G. And this is equivalent to Gx consisting of semi-simple elements. So this is a very interesting statement. It says that if your X is semi-simple, but if it is not regular, then it will contain some unipotent elements in its centralizer. Because the equivalence here says that if X is not regular, then Gx will consist of elements which are not semi-simple. But once you have an element in some group, its semi-simple part and unipotent parts have to be there in the same group, and therefore there has to be a unipotent element in the centralizer of your X. And this final statement is also similar to the third statement or the second statement, that all roots have a non-trivial value on your element X. So this is again seen very easily for our SLN case. For SLN, our roots were simply a chi-ij, where you are choosing an ith element, a jth element, and you take the quotient. You take tj, ti upon tj. And this statement says that Ti upon Tj is never 1 whenever you take any two I and j. And therefore, we have that all the entries in the regular semisimple element, all the eigenvalues will have to be distinct. So this is when X is a semisimple element, okay? And also remember the above statement that X in G is regular if and only if its unipotent part is regular in the connected part of the centralizer of the semisimple part. Okay, so now we come to the regular unipotent elements. So this is something which is studied quite at length by Steinberg in his so this thing about regular unipotent elements is studied by Steinberg in his IHES paper, and I think the title of the paper is Regular Elements in Semisimple Algebraic Groups. And these are some very interesting results that are proved here in this paper. And as a corollary, he also proves one statement by Sayre, something to do with Galois cohomology. So I urge you to go and take a look at the paper or take a look at the MathSciNet review. It is such an interesting result that Sayre has included that paper with Steinberg's permission in his book on Galois cohomology. Okay, so that tells us about the importance of this paper. If you are looking at unipotent elements alone, then it's a closed irreducible subvariety of capital V of G of codimension R. You collect all unipotent elements in G. This is a very large subvariety. Its codimension is R. That means its dimension is n minus R. If you are looking at n to be the dimension of your group G, if you are looking at n as the dimension of the group G, then the dimension of this variety, this is an irreducible variety of codimension R in the group G. So the set of unipotent elements. The set of semisimple elements is a dense subset of G. So that's an even more bigger subset. But this is a closed irreducible variety of this particular codimension. Moreover, the regular unipotent elements, they form a single conjugacy class in G. So all regular unipotent elements in G are conjugate in G. This class is an open subset in capital V. The set of regular unipotent elements is an open subset in capital V, the variety of unipotent elements in G. And its complement has codimension at least 2. So the complement of this conjugacy class is 2 or more. The complement has codimension 2 or more. That means this class is non-empty. In particular, you have regular unipotent elements in any semisimple algebraic group G. Okay, so the complement has codimension at least 2 means this variety, this open subset should have dimension 2 or more. And therefore, there are regular unipotent elements in a semisimple algebraic group G. Okay, there exist regular semisimple elements in semisimple algebraic group G. One can modify this and also say that this thing holds for a reductive group. You can look at you can take your group and take its derived subgroup, and you will have regular unipotent elements in the derived subgroup. And anyway, your group, reductive group, is going to be an almost direct product of the central torus and the derived group, the semisimple part. You will have regular unipotent elements in the reductive group as well. And this gives rise to this very interesting corollary that you take a regular element and you go to its central semisimple part. If your X is any element, you take the semisimple element, then you are going to get a semisimple element. Okay, so this map is actually a map from regular classes to semisimple classes. If you have two elements which are conjugate, their semisimple elements, their semisimple parts are going to be conjugate. by the same. We have seen that the decomposition remains valid for any endomorphism. So in particular for inner automorphisms, it will remain valid. And therefore, by conjugating X, you are simply conjugating the semisimple part and the unipotent part. Okay. So sending X to its semisimple part defines some function from the regular classes to semisimple classes. But this map is a bijection. So let's see why this map is onto. We want to say that every semisimple element is semisimple part of a regular element. Okay. We are claiming that you take any semisimple element, it is semisimple part of a regular element. And how does one see this? So you take the centralizer of your semisimple element. Suppose you have only excess to begin with. You take the centralizer of excess. That's a reductive group. You take the connected component if you have to. So you get a connected reductive group. Now the above statement gives you that a connected reductive group has to contain a regular unipotent element. So you have a regular unipotent element in the centralizer of your excess. Okay. So call that element XU. We started with a semisimple element XS. In its centralizer, we obtained a regular unipotent element and we took the product, we take the product of these two. So you have XS and you have XU. Now, XS is semisimple, XU is unipotent, and these two commute because you are taking XU from the centralizer of XS. Okay. Therefore, when you take the product of these two and call that element as X, the semisimple part of the X has to be XS and the unipotent part of X has to be XU. This is because the semisimple part and unipotent part are unique with respect to some properties. What are those properties? The properties are that your element is product of semisimple and unipotent, and moreover they commute. All these properties are satisfied by XS and XU, and so the semisimple part of XS XU has to be XS. The unipotent part of XS XU has to be XU. And therefore, we get that the semisimple part of X, which is the product of XS and XU, is XS. Moreover, you have taken XU to be regular unipotent element here in GX naught. And therefore, the X you have thus obtained is a regular element. Okay, so starting with any semisimple element, we have obtained a regular element whose semisimple part is XS. So this map is now onto. Starting from regular classes, we can get all semisimple classes. And further, this map is also one-to-one. That is because when you have, suppose we have X and Y, and their semisimple classes are conjugate, then you can do the same thing. What you can do is that you have, suppose X and XS and YS, the semisimple parts, are conjugate. We want to prove that X and Y are conjugate, them being regular. So if the XS and YS is conjugate by some element G, then you change your Y by that suitable conjugation so that you have two regular elements having the same semisimple part. And once again, you look at the corresponding Z centralizer of that semisimple part, look at its connected component. The unipotent parts of these two elements will have to correspond to regular unipotent elements in the corresponding reductive group. But the regular unipotent elements form a single conjugacy class. That's what we have here. And therefore, we will have that the corresponding elements have to be conjugate. So the complete statement is that every semisimple element is semisimple part of a regular element. Okay. Moreover, if there are two regular elements whose semisimple parts are conjugate, then these two elements are already conjugate in your group. So this is a very nice statement. And further, there are these very interesting statements again. we have seen already that this set of regular unipotent elements is open in the set capital V of unipotent elements. If you were to look at all regular elements in G, that set is open in G, and it may not be irreducible, but its each irreducible component, its complement may not be irreducible, but each irreducible component of the complement has codimension 3. So this is a very precise statement. Here we had a statement saying that when you were looking at only unipotent elements, regular unipotent inside unipotent, the complement may have dimension at codimension at least 2. But in general, if you are looking at the regular elements in the whole of G, then the complement has codimension 3. And I also told you that when you had semi-simple regular element, there is a unique maximal torus which contained it. In fact, we will have a similar statement for unipotent elements. But in general, if you have a regular element, then the number of Borel subgroups containing it is finite. So when you are looking at semi-simple elements, you would look at the maximal tori containing it. When you have unipotent elements, you will look at the number of unipotent subgroups, the capital U that we had, the unipotent part of a Borel containing it. But if you are looking at a general element, you will look at the Borel subgroups which contain it. So if your element X is regular, then the number of Borel subgroups containing that is finite. And in fact, one can write down this number precisely. This is equal to the quotient of two while groups, the quotient of the orders of two while groups. One is the while group of G, other is the while group of the connected centralizer of the semi-simple part of X. So you take the connected centralizer of the semi-simple part of X, compute its while group. It's a subgroup of capital G because you can assume that there is a common maximal torus in both of them, and therefore you compute the quotient of this subgroup in while group of G. That cardinality is precisely the number of Borel subgroups containing the regular element X. And moreover, now if you were to take your element X to be unipotent, then its semi-simple part is trivial, right? If your X is unipotent, its semi-simple part has to be trivial. So the centralizer of the trivial element is again the whole group G. So this number becomes 1. If you are looking at a regular unipotent element, then the centralizer of its semi-simple part excuse me, there was some disturbance at home. If you were looking at a regular unipotent element, this semi-simple part of this unipotent element will be the trivial element. Then we will compute the centralizer of the trivial element, which has to be the whole group G. And therefore, the while group of that is again the whole while group. So this subgroup of the centralizer of the semi-simple part connected component is the full while group. So this number is simply 1. Therefore, whenever you take a regular unipotent element, it is contained in a unique Borel subgroup. And in fact, one can explicitly write down, once you write down an element, unipotent element, you can tell just by looking at it whether it is going to be regular or not. And remember that this capital U, we had written it as product of positive product over positive roots of all the root subgroups coming from the positive roots. So if you were to write your element X as product of those root group elements, which are given by some one parameter subgroup. So these C alphas are elements coming from the base field GA, and X alphas are the corresponding one parameter maps. Okay, so your X is going to be unipotent if and only if for every simple alpha, the corresponding C alpha is non-zero. Okay, we don't care what happens when your alpha is not simple. For all simple alpha, the C alpha has to be non-zero. That is equivalent to having your element to be regular. So these are some of the very nice statements, and we have done some such computations of number of Borel subgroups containing a given unipotent subgroup, depending on the partition of n for SLN and so on. And this theorem would, this observation would tell us how to compute the number of whether or not your element is unipotent regular, and then there will be only one Borel subgroup containing your element. Now we come to G sigma. So this was all the study about regular elements in the group G and its K-bar points. We are interested in looking at G sigma, the finite groups that we have. So I told you that the Jordan decomposition holds in G sigma, and in fact the semi-simple elements and unipotent elements can be computed by, it can be understood by looking at their orders. The unipotent element has to have the order in this finite group, which is a power of P, and the semi-simple elements have to be of those elements whose orders are co-prime to P. So P is your characteristic of the base field, and you are looking at the finite group G sigma. Any element which is a P element, whose order is a power of P, is a unipotent element, and vice versa. And any element whose order is a P prime, which is a P prime element, its order is co-prime to P, then it is a semi-simple element, and vice versa. Okay. So for instance, inside SL2F2, SL2F2 is isomorphic to S3. And inside S3, you look at orders of the elements. There are 3 reflections of order 2. Those all have to be unipotent elements. And then there are 2 elements of order 3. They are both the semi-simple elements. Here we don't have a general element. Here we don't have an element whose order is neither co-prime to P nor power of P. It can happen. You may look at SL to F3, which is a group of order 24. There you will have some elements whose orders are 4. They will then be semi-simple. Remember, the F3 is the base field. So characteristic is 3 and 4 is co-prime to 3. There will be some elements whose orders will be 3, and there will be some elements whose orders are 6. So these order 6 elements are neither semi-simple nor unipotent. These are the general elements which will be product of semi-simple and unipotent. Okay, so for finite groups, we understand the semi-simple elements and unipotent elements by looking at the corresponding orders. And this is one nice statement, that G sigma does contain a regular unipotent element. So the statement which I had, that when you are looking at semi-simple conjugacy classes which are fixed by sigma, that does contain an element which is fixed by the map sigma. That holds for regular unipotent, that holds for regular unipotents also. We know that there is a single class. If you are looking at the group G, then regular unipotent elements are all conjugate. So there is a single class, so it has to be invariant under sigma. And once you have it invariant under sigma, then it will have some element defined below. And this is again another very interesting statement, that if your group G is simple, then the number of regular unipotent elements of G sigma is cardinality G sigma upon Q power R. So the total, so this is about the regular unipotent elements. Whereas if you are looking at unipotent elements alone, the total number of these is Q power dim G minus R, which is same thing as Q power dimension V. I told you that there is this vector, there is this subvariety capital V consisting of unipotent elements of codimension R. So the dimension of this subvariety V is dimension G minus R, because variety V has codimension R. And if your V was an affine space, just as we had for the conjugacy classes in simply connected groups, if it was an affine space, then we would easily compute the number of its fixed points under sigma. But it is not quite an affine space. and therefore this is not a very trivial statement. This statement requires some proof, but this is indeed true. So if you were to look at all unipotent elements, for instance, inside GLN, that would be q power n square minus n. Such a beautiful statement. And that is also the same thing as the number of unipotent elements in SLN. Any matrix in GLN which is unipotent is contained in SLN. Its determinant is 1, and the number does remain the same. Dimension G decreases by 1, rank decreases by 1. Okay, so these are some very nice statements which were done in that paper, which is more than 50 years back. And there are some further interesting statements, but to state those statements, one would require higher machinery. One would need to talk about good primes, bad primes, and so on, corresponding to your group G. So there are some primes called torsion primes and so on, which play quite an important role. You may remember the theorem of Richardson, which I had stated in the previous lecture, which said that when you have a group G defined in characteristic which is good for G, then the number of unipotent conjugacy classes is finite. This was the result that we mentioned, and then Lustig proved it for all characteristics. So the good primes and bad primes did already come there when we were studying unipotent elements, and it does come quite prominently, and it becomes very technical when we have to even state these very interesting results about unipotent conjugacy classes. But quite a lot of work is done on unipotent conjugacy classes, not just over K bar, but also over G sigma by several people. And a very good reference for this is the AMS survey monograph by Liebeck and Seitz. The title of that is this. It's a very nice book and very good reference book. Unipotent and nilpotent classes in simple algebraic groups and Lie algebras. This is published by AMS in 2012. I think I will stop here at this point. I will be happy to take questions. Thank you very much.
Thank you, Shripad. Thank you for a nice lecture. Let's first thank Shripad for his beautiful lectures, and then of course we can continue discussing.
Thank you.
Thank you. So there are basically two kind of problems here if you want to compute the conjugacy classes actually in something, right? For example, SLN, whether you want to see inside this bigger group inside GLN or you want to go over Q bar for a particular group.
But for SLN, it is equivalent.
Right. For SLN, it is equivalent.
If
right?
the elements are semi-simple, then the thing is same.
Mm-hmm. Yeah.
But in general, it can be different. But now we know how it all looks like.
Right.
Now it is quite easy to understand.
Yeah.
So that way, it's a very well studied thing. All that one has to do is to go and read these papers. This whole book is really a collection of very nice articles.
Right.
But yeah, true. Meaning in general, if you wanted to study conjugacy classes in G sigmas, then you would have to understand it above and then see how many classes it decomposes into as you come down.
Right.
Yeah. But these are also some innocuous statements. The Jordan decomposition tells us that if you take two commuting elements, one of which is semi-simple, other is unipotent, then the semi-simple part of the product is the semi-simple element and unipotent part of the product is the unipotent element. So that is, very nice result. And they don't even mention, Springer-Steinberg don't even mention this. I think it is taken as a very basic statement. Shall I stop sharing?
At some point, maybe Shripad, you can give a little more of these papers. If at later point there is some more lectures.
Yes, I think it will be good. Maybe we could collect some people and have a discussion about that. Yeah.
I mean, this small book memoirs could be done from beginning to the end.
Yes.
No,
Yes.
possible.
Yes.
It's not that large, and it
No.
is self-contained.
Yes.
So, if you were to run such an activity, I think it would be useful to many people.
Yeah, it will be useful to me definitely. Meaning, I would understand several things.
Yeah, no, I think Anupam will be happy, and
Yeah. Sure. I mean,
nice.
explicitly when writing the conjugacy classes for orthogonal groups, symplectic group, etc., they are quite tricky in general.
Yeah, right, yes.
It's not. I mean, like for GLN, we understand them via rational canonical form and things like that. It's somewhat very easy to say, but these things get complicated because then you have some kind of sign and all this kind of stuff gets involved.
I think this is
So,
Springer-Steinberg has classical groups.
right, yeah.
Maybe when you were coming to TFR, there was you people read some paper of Milner or so, CTC Wall.
Yeah, wall basically. Yeah, which is
Classical
a
groups.
tricky paper in itself,
Sorry,
which is a difficult paper to read in itself.
no, but I think Springer-Steinberg is more easy to read.
Yeah, Springer Steinberg is much easier that way.
Yeah.
And it contains beautiful results, meaning the number of
Yeah.
unipotent elements and such very nice result. You also told me about number of maximal tori,
Yeah.
meaning some given in some formula. Nice formulae.